In 2D, we're going to look at the binomial theorem. And in the binomial theorem, and that's when we have two terms, let's say a plus b, and it's raised to some power. So a plus b quantity to the nth power. Now we already done this a few times in previous sections. Like we know that a plus b to the 0 power is equal to 1, because anything raised to 0 power is 1. We know that a plus b to the first power is equal to just a plus b. I don't have to write to the first degree. And in section 2a, we learned that a plus b squared is equal to our first term, which in this case is a squared, plus 2 times our first term times our last term, plus our last term squared. Now let's try a plus b cubed. It's a little bit more difficult, but we could figure this out with the knowledge we have right now. We could rewrite this as a plus b times a plus b squared. Now a plus b squared we just figured out above, so let's substitute that in. And as we learned in the last section, now we're going to take this a and distribute everything in the second parentheses, giving us the following. And then distribute the b to everything in second parentheses. So that will be a squared b plus 2ab squared plus b cubed. Finally, we'll need to add our like terms. Okay, that was doable, and we were able to figure it out with our skills that we know up to now. But what if I asked you a really harder question? What if I asked you to figure out something like a plus b to the 20th degree? Now, I'm not going to want to sit here and multiply this all out. That would take a full page, maybe even 2 pages. So there has to be a better way to solve complex problems like this. And we're going to do that by using something called the binomial theorem. But before we do this 3-step process you see above, we need to know something called Pascal's triangle, which plays a big part in step 1 of the binomial theorem application. So what is Pascal's triangle? Well, simply it starts at this row 0, you have a 1. And then the next one, you bring the 1s down. So you have 1 and 1. For our next row, which is row 2, we're going to bring the 1s down on the outside. Outside terms are first and last terms always 1, so we just bring that 1 down. Now we're going to add the 2 middle terms together to give us 2, and then bring the 1. Continuing this process, middle terms added, and bringing the 1 down. So bring the 1 down. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Bring the 1 down. You can continue in this pattern as many times as you want, continuing row after row after row following the pattern. Now, I'm going to use some terminology in this. So first thing we need to make sure you understand is what row that we're looking at in Pascal's triangle. So row 0, and how this relates to our binomial. Remember a plus b raised to the 0 power? That gave us an answer of 1. Notice that coefficient corresponds to the coefficient of 1. In row 1, this corresponds to if we take a binomial and we raise it to the first degree, a plus b to the first degree, which you recall from the first thing, that's a plus b. Now notice those coefficients are 1 and 1. In row 2 corresponds to a plus b squared, which remember is a squared plus 2ab plus b squared. And notice the coefficients there are 1, 2, and 1, which corresponds to this row. And you can continue this on for as any row that you want. So that's why we use Pascal's triangle in our binomial theorem process that we're going to be doing. Okay, so let's try this to an actual problem. So first thing you need to do is always recall what Pascal's triangle looks like. And you need to figure out Pascal's triangle to the corresponding row that we're looking at. So since I'm looking at cubed here, I need to go to row 3 on Pascal's triangle. And that's going to tell me my first step, which is the coefficients that is determined by Pascal's triangle. So in this first term that I'm going to write, my coefficient would be 1. My next step is to take the first term in the binomial and raise it to the degree that I'm doing. So I'm going to take the first term and I'm going to raise it to the 3rd degree since I'm doing a cube function here. So that makes my first term x, so this will be x cubed. And then in the green, we have times by the second term raised to the 0 power and increase the degree by 1 until I get to my nth degree, in which this case is the 3. So that's going to be 5 to the 0 power. Okay, plus now I move on to my next term. So starting in Pascal's triangle, the second term was 3. I look at the first term in the binomial, which is x. And I'm going to raise that to the second degree this time, so it's going to be x squared. Now I'm going to times that by the last term binomial, which is 5, raised to the first power. Continue the process to our next term, so term 3. The third number in that row for Pascal's triangle is 3, times by my first term of the binomial, which is x, raised to the first power, times by my last term in the binomial, which is 5. This time we're going to square 5. So notice we're increasing the power of the 5 and decreasing the power of the x term. Plus, we're down to our last row of last number in Pascal's triangle for this row. So we add a 1. Then we take our first term of x and raise it to the 0 power. Times that by our last term of the binomial, which is 5. Raised to the third power. Some things I want you to notice. Notice in the red, we have 1, 3, 3, 1. That corresponds to our Pascal's triangle for row 3. Also, notice that the x terms start at degree 3 and decrease by 1 each time. And then the constant, that y term, starts at 0, increases by 1 each time until we get to the 3 as our ending degree. Now, all that's left to do is simplify. 5 to the 0 power is 1, so we times all that together and it ends up with x cubed. And then we have 5 times 3 times x squared. Well, that's just 15x squared. Plus 5 squared is 25. 25 times 3 is 75 times x, so that would be 75x. Remember, x to the 0 is just 1, so all we have here is 5 cubed, which is 125 times 1. So our final answer you will see in the box. Okay, I'm going to do this example. Notice I'm still doing row 3, so I'm just going to use the Pascal's triangle from above. So my first coefficient is 1. My first term this time is 2x. That all of 2x need to be cubed. And my last term of the binomial is simply 1, so that 1 needs to be raised to the 0 power. And then moving on to our second term, which will be our second number in Pascal's triangle, which is 3, times by our first term in the binomial, which is 2x, raised this time to the second degree, times by our last term of 1, raised to the first degree, plus, moving on to a third term, so that's going to be a third number in Pascal's triangle in that row, which is 3, times by our first term in the binomial, which is 2x, raised to the first power, times by our last term in the binomial, raised to the second power. Plus, now we're on to the last term in our Pascal's row, so that's going to be coefficient of 1. Our first term in our binomial given problem was 2x, and we're going to square that. Raise that to the 0 power. And then we have 1 raised to the third power. Simplifying each of these terms, I'm going to remember that you have to distribute that 3 to every one of the base. I'm going to write that so you can always remember to do that. So that gives us 2 cubed times x cubed plus distributing the 2 to each of those. And 1 to the first power is just 1, so I don't need to write that. Now 3 times 2x times 1, so let's just go ahead and simplify that down. And that's going to give us 6x. And anything raised to the 0 power is 0, so all I have left in that last term is 1. So finally, this is our final answer. For example C, let's how we apply this if we have a binomial that is a subtraction. So again, I'm looking at the 5th row, so I need to figure out my Pascal's triangle all the way down to the 5th row. Next, I'm going to rewrite this binomial x minus 2 as an addition, so it looks like the examples A and B we did before. So I can rewrite that as x plus a negative 2 to the 5th. Now it's very easy to see my first term is going to be the x, and that's what I'm going to start with the degree phi and decrease the power by 1 each time. And my second term is going to be negative 2, so please make sure you take the negative 2 with each term. And that's what I'm going to start with the 0 degree and increase by 1 for each of my terms. Now we're ready to apply our binomial expansion. So looking at Pascal's row 5, my first coefficient is 1. My x is raised to the 5th degree. My negative 2 is raised to the 0 degree. Plus, moving to our second term, so it's the second number in this row on Pascal's triangle, which is 5, times x to the 4th degree, times by negative 2 to the 1st degree, plus our third term in Pascal's triangle of 10, times by x to the 3rd degree, times by negative 2 to the 2nd degree, plus our fourth term in this row of Pascal's triangle, which is also 10, times by our first term in the binomial, which is x squared, times by our second term, negative 2 to the 3rd degree, plus our fifth term in Pascal's triangle, which is 5, times by x, times by a negative 2 to the 4th degree. Our final term I'm going to try to fit in over here is going to be plus 1 from Pascal's triangle, times our x to our 0 power, times by negative 2 raised to the 5th power. All right, let's simplify this down. Our first term will simplify down to x to the 5th. Negative 2 to the first degree is negative 2, times that by 5 gives us negative 10x to the 4th. Negative 2 squared is positive 4, times by 10x to the 3rd gives us 40x cubed. That gives us negative 8 times 10x squared, negative 80x squared. And then we have a positive 16 times by 5x squared, which is equal to a positive 80x. Now we take a negative 2 raised to the 5th power times 1, because x to the 0 is 1, and that gives us a negative 32. Our binomial consists of a negative. That's a wonderful pattern that shows up. Notice our signs for each term alternate from positive to negative to positive to negative. That will always occur when you have a binomial that is a subtraction. Okay, example D. Rewrite this as a first term plus a negative term, so you know that our second term is negative 2. I'm going to use the Pascal triangle above, and for the fourth row, it's going to be the one circled in black. So I'm going to use coefficients 1, 4, 6, 4, and 1 in problem D. Coefficient from Pascal's triangle would be 1. 1 times that by my first term of 3x raised to the 4th degree, times by our second term, which is negative 2, raised to the 0 degree, plus our second term in Pascal's triangle, which is 4, times by 3x raised to the 3rd degree, times by negative 2 raised to the 1st degree, plus our third number in this row of Pascal's triangle, which is 6, times by our first term of 3x squared, times by our second term, which is negative 2, raise that to the 2nd degree, plus 4 from Pascal's triangle times 3x raised to the 1st degree times by negative 2 raised to the 3rd degree, plus the last number in this row of Pascal's triangle, which is 1, times by our first term of 3x to the 0 degree, times by our second term of negative 2 to the 4th degree. But not least, it's time to simplify. So we have to distribute that power of 4 to both of the bases, the 3 and the x. So I write that as 3 to the 4th degree times x to the 4th degree. And then plus, distribute, we have 4 times a negative 2, which is negative 8. Distribute the 3. 6 times 4 will give us 24. And then distribute the 2 to each base, the square to each base. For our fourth term, we're going to take negative 2 and cubed it, which is a negative 8, times it by 4 and times it by 3x for a negative 96x. And then a negative 2 to the 4th degree is a positive 16 times by 1 and 1, so that's 16. Finally, let's simplify this down. 3 to the 4th is 81, x to the 4th. Our second term, when simplified, becomes 216x cubed. Term 3 becomes positive 216, x to the squared, minus the 96x plus a 16. And there you go. This is how you do binomial expansion.